Today I will present core strategies for low cost, Ladle castable althorn, and GO alumina spinel system in this deck. Low cost does not mean choosing the cheapest ingredients, it means optimizing total cost of ownership, including installation efficiency, dryout safety, downtime, repair frequency, and life stability. We will take an engineering-first approach, focusing on how formulation choices, installation discipline, and operational integration jointly determine cost per ton of steel. This presentation is prepared and presented by Wuhan Xiandair Chemical Co., Limited, copyright Wuhan Xiandair Chemical Co., Ltd., all rights reserved. On this slide I redefine low cost as TCO, not unit price. Unit price is only one component of the total cost stack. In many castable systems, raw materials account for a large share of direct cost, often around approximately 80%, but the real multipliers come from installation dryout, and especially downtime and opportunity cost. So the decision metric should shift toward cost per ton of steel produced, because that automatically captures life, repair frequency, and productivity loss. The main takeaway here is, once we look at TCO, we see many savings opportunities that are invisible if we only debate unit price. Here I explain the method I will use throughout the deck. On 3-layer framework. At the surface layer, we discuss direct levers and actions, raw material choices, workability, and practical measures. At the middle layer, we discuss trade-offs and performance boundaries, especially the triangle of corrosion versus penetration versus thermal shock. At the deep layer, we turn the strategy into an executable system, NVSS, including roadmap validation and rollback plan. This framework ensures our recommendations are robust, validated, and reversible, so improvements are scalable rather than one-off success. This slide frames the global picture. Different regions start from different constraints: raw material availability, cost structure, environmental regulation, and steel cleanliness requirements, so their historical roots differ. However, the convergence is clear. Everyone is moving toward high-performance, sustainable solutions, and the global trend is replacing chrome-based refractories for environmental reasons. China tends to leverage abundant bauxite, magnesite with cost-driven natural, synthetic blends. US/EU emphasizes high-purity synthetics, recycling loops, and digitalization. Japan, Korea focus on purity for clean steel, advanced binders, and prefabrication. The message: the destination is shared CR-free, long-life system-based solutions. Here we connect the cost stack to decision logic. Raw materials dominate direct material cost, which is why substitution appears as a major lever. But operational costs, downtime, and energy often drive the biggest indirect savings. A key performance indicator is overall lining consumption in kilogram per ton of steel, because it reflects life and maintenance effectiveness, so we must balance initial cost against in-service performance. The diagram emphasizes that TCO is the sum of material cost and process service cost, where manufacturing, installation, dry-out energy, time, and downtime can dominate outcomes. The decision logic is the reform: optimize both the dominant material cost and the high-impact operational multipliers. This slide gives a portfolio view. Multiple levers reduce TCO, but they have different risk profiles. High-impact strategies often require greater implementation discipline. In the lower-risk, high-impact area, we typically start with binder strategy evolution, PSD, rheology optimization, and operations monitoring to reduce over-maintenance. Higher risk but high-impact levers include raw material substitution, prefabrication, modularization, and recycling loop integration. Doping and phase control can be useful, but usually functions as a fine-tuning lever. The main message: TCO reduction is achieved by a portfolio sequence from controllable foundational optimizations to system-level changes. This slide explains the first formulation lever: substitution. The strategy is to replace high-purity synthetics with cost-effective alternatives in select areas, such as using bauxite or brown-fused alumina. 2. Partially replace white-fused alumina. The practical method is zoning. Use premium materials where wear mechanisms are severe, like slag line or impact zone, and use blended systems in moderate wear zones such as wall, bottom, where the risk profile is manageable. The key risk is performance variability, so rigorous batch validation is essential. Done correctly, strategic substitution can cut cost without compromising critical performance. Now binder strategy, the evolution is clear. High cement gives LCC gives you LCC gives cement. Free, mechanistically. Reducing Ca input helps avoid low melting, calcium aluminate phases and improves high temperature performance. The benefit is higher purity, stronger hot strength, and better slag corrosion resistance for clean steel. Advanced cement, free binders such as sol, gel, or hydro-table alumina systems become attractive, though they require tighter process control. The key message is that binder upgrading is one of the most powerful routes to enhance purity and high temperature performance, while still supporting cost reduction through life improvement. This slide covers micro additions for microstructure engineering. The principle is small, precise additions, small dose verifiable, reversible use to tune sintering, expansion behavior and toughness. TO can act as a mineralizer to support in situ spinel formation and improve volume stability, though it may affect slag interaction chemistry. Microsilica provides gel-type binding and can balance expansion, but dosage must be controlled to avoid low melting phases above certain levels. SRL improves fracture toughness through stress-induced phase transformation, but increases material cost. Overall, doping is a sophisticated tool for targeted improvement, not a substitute for correct system design. Here the focus is packing and flow. The goal is maximum packing density with minimum water and binder, often guided by multi-model PSD models such as Andreessen. If PSD and rheology are not controlled, we see segregation bleeding or full set, which later become penetration paths or spalling initiation sites. The slide emphasizes a validation trio: flowability, bulk density, and mechanical strength, cold, hot, more. The key takeaway is that optimized packing is fundamental. It simultaneously supports workability, density, and final strength, enabling both performance and cost control. This slide connects formulation to execution. A good formulation can fail if installation and dry out are not precisely controlled. Critical parameters like water ratio and mixing energy have narrow optimal windows. The process chain water control, mixing energy, time placement, open time, setting, and demolding must be disciplined. For anti-explosion strategy, we use mechanisms such as organic fibers that create escape channels as they melt, burn out, plus heating curve optimization to manage pressure build up. Validation methods include permeability testing, controlled bake out trials, and even acoustic emission monitoring. The message: installation discipline is a primary determinant of TCO. Now we move into service mechanisms. In service, failure is driven by coupled chemical and thermal mechanical stresses. A key design goal is forming a stable, self-protective slag interface layer. The failure mode map helps prioritize mitigation: thermal stress-driven spalling versus chemical attack-driven corrosion penetration. Mitigation may involve toughening agents like throw, PSD control, higher purity spinel, or in severe cases prefabricated solutions and system-level redesign. Also note the role of in-situ spinel formation. Controlled expansion can help seal pores and resist penetration. Ultimately, balancing resistance to corrosion and thermal shock is central to low DLE lining design. This slide introduces MVSS. The key idea is that we need a holistic approach integrating the entire life cycle, not just selling a product, but delivering a controlled performance outcome. The closed-loop system links formulation, installation, operations monitoring, and recycling with continuous improvement feedback. Implementation is organized into deliverable packs: formulation pack with customized recipe and QC specs, process pack with SOPs for mixing, installation and dry out, monitoring pack with sensor specs models, dashboards, and recycling pack with reclamation and reuse procedures. MVSS makes performance and cost outcomes scalable, not accidental. Here the low carbon logic aligns with TCO logic. Extending lining life is often the most effective. The carbonization lever because it reduces consumption of energy, intensive raw materials, and relining activities. A closed recycling loop further reduces raw material and energy consumption, are commonly used. A illustrative estimate is that recycling 1 ton of refractory can avoid on the order of about 1 ton of CO emissions. Depending on the boundary conditions, the life cycle comparison chart emphasizes standard life versus extended life plus recycling, where CO reduction becomes significant. Longer life and recycling are not extra work. They are strategic levers for both cost and carbon. This slide is crucial for credibility. Aggressive cost cutting has clear performance limits, and understanding boundaries is critical for safety. Therefore, we must define exit criteria and rollback plans. The table provides 3 representative scenarios: accelerated corrosion driven by aggressive slag or incorrect zoning, catastrophic spalling from rapid thermal cycling or excessive densification, and installation failure from incorrect water ratio or aggressive dry out. Each has a countermeasure and a rollback plan, such as upgrading purity in the affected zone, introducing toughening and adjusting heating, or in severe cases halting operations and relining. The key takeaway: robust risk management with clear exit criteria is essential for any cost optimization program. This slide defines what we need to tailor and VSS precisely. The 6 inputs are ladle fleet capacity and geometry, process root buff, EAF and refining, steel grade mix, slag chemistry and heat oxides, operational data such as temperatures, holding times, cycle frequency, and performance targets such as desired campaign life and cost per ton goals. These inputs allow us to model performance and quantify TCO savings. The key message is that a data-driven approach starts by defining operational context and targets. Then, we design and validate accordingly. To conclude, a systematic TCO-focused approach delivers sustainable cost reduction, and VSS provides a clear stage, gated path to implementation. And the most effective next step is a collaborative workshop to define a tailored validation plan. The staged goals are also clear: first cost reduction, then life extension, then global benchmarking performance. This presentation is prepared and presented by Wuhan Xiandair Chemical Co., Ltd., and the deck reflects a technical interpretation and engineering recommendations while respecting third-party ownership. Our intent is to translate these strategies into measurable operational improvements. Finally, the appendix provides a metric yardstick for objective evaluation. Standardized metrics connect material properties to operational and economic outcomes. Campaign life in heat captures longevity. Specific consumption in kilogram per ton of steel is a core ETCR metric. Corrosion rate in mm per heat and penetration. Depth in mm quantify mechanism, level behavior, and cost per ton combines material cost with performance outcome. The key takeaway is that consistent and clear metrics are the foundation of any data-driven improvement program. Without a shared yardstick, optimization cannot be validated or scaled.